Okay, so we're now going to look at problems with a horizontal and a vertical component, which effectively means something that's been released at an angle. So we might be talking about throwing a basketball or a netball into a net, but something that's on a parabola. So we may have, and I'm just going to draw it like on a pair of axes because I just think it's the easiest to visualise. So something might have been released at an angle with an initial velocity, u. So if it's released at the angle, it's going to create an arc like that because we have gravity acting downwards and it's our angle alpha. So gravity acting downwards is obviously going to influence the velocity as it's going and then cause it to come back down. So because it's being released at an angle, we can resolve this velocity horizontally and vertically. So we can sort of create ourselves a right angle triangle of the initial velocity. So we've got our horizontal velocity and our vertical velocity. So with our horizontal velocity, so this is us resolving horizontally, well, I know cos of theta is going to be equal to our horizontal velocity over our overall initial velocity. So therefore our horizontal velocity is our overall initial velocity multiplied by cos alpha. Move this out of the way. And our vertical velocity, so we're going to resolve vertically. Well, if this is a right angle triangle, then this is going to be sine of alpha will be equal to our vertical velocity over our overall initial velocity. So therefore our vertical velocity is the overall initial velocity multiplied by sine alpha. So this tells us obviously the rate at which it's travelling vertically and horizontally. Now in the book it kind of says, you know, you can know it as this and know it as that. And you can learn it, but you can always set up a right angle triangle if you need to. So what slide number are we on? 1, 2, 3, 4, 5, 6. So slide 6, we're sort of summarising this information. So slide 7, looking at example number 1. And I'll move my paper up so you can see a little bit better. Oh, sorry, I've always got kicked off my chair because my cat is sitting behind me and I almost slid off. Right, anyway, back to normal. A particle is projected from a point on a horizontal plane with an initial velocity of 40 metres per second at an angle alpha above the horizontal, where tan alpha is 3/4. So let's first of all actually sketch out this problem. Now, we don't have to actually do like a proper pair of axes. We can just draw the horizontal, but I just find it easier personally, but you don't have to draw this line if you don't want to. So I know that it's been released at 40 metres per second and it's going to come over in an arc like this. I have gravity acting downwards and I have an angle alpha. Now what I know about this angle is that tan alpha is equal to 3/4. Now we know it's an acute angle, so we can use this to work out our sine alpha and our cos alpha. Well, that's the opposite and that's the adjacent. So sine is going to be 3/5 if you're looking at a Pythagorean triple. Obviously, square that, and square root. And then adjacent over hypotenuse. Okay, perfect. So we've got sort of our information set up, ready to approach the problem. A, Find the horizontal and vertical components of the initial velocity. So effectively what that means is find what the horizontal and the vertical velocity is to start with. So I'll resolve horizontally first. So UH is 40 times by cos alpha. Obviously would be cos of alpha is equal to this over 40, so 40 cos alpha. So 40 multiplied by 4/5 from what we've worked out previously, which is 32 metres per second. If I resolve vertically, then my vertical velocity is 40 times by sine alpha, which is 40 multiplied by 3/5, which is 24 metres per second. So this particle, even though it's being projected 40 metres per second at the angle alpha, that particle is travelling in the first sort of second at vertically 24 metres per second and horizontally 32 metres per second. Okay, part B. Given that the vectors I and j are unit vectors acting in a vertical plane, horizontally and vertically respectively, express the initial velocity as a vector in terms of I and j. So all this means is we're expressing this initial velocity in terms of these two components. I is our horizontal and j is our vertical. So therefore u is 32i plus 24j metres per second. So all it means is to write this as a component vector, because obviously this is the initial velocity, okay? Obviously the velocity changes over time because of the impact of gravity. We're not worrying right now about those kinds of problems, okay? I've just put them into the picture so that you can see how we're going to set up for the problems that we'll do in a minute. You might get a cat in the screen in a minute because my cat is deciding that this is too boring and that he needs to get involved. Yes, buddy. Okay. Right. Example number 2. Can you please get off? Example number 2. A particle is projected with a velocity u equals 3i plus 5j metres per second. So they've given it to you as a component vector already. So it's giving you your horizontal and your vertical components of the initial velocity. What you've always got to remember with this, when it starts up the problem, it is talking about the initial velocity. Evidently, the vertical velocity is changing over time, even if the horizontal isn't. So you just need to be aware when we're talking about these problems, this is only the initial velocity that we're talking about. So where I and j unit vectors, it always clarifies that information in case you struggle with vectors, I assume, so that you're still able to approach this problem, and so that you don't think it means anything different. So you might, if obviously you're doing your A-levels as normal and doing your maths exam with your further maths exam, I suppose it's so that you don't confuse I with being a complex number component, for example. So the question says, find the initial speed of the particle and its angle of projection. So let's just sketch this problem to start with. My cat on my lap is making me do dodgy work. That was my cat pushing my hand. Right, so that's u. We don't really know much information about u as a whole. What we do know is that the initial velocity is 3 in the direction of I and 5 in the direction of J. So because we know that this is a right angle triangle, we can work out the initial speed simply using Pythagoras. So u is going to be the square root of 5 squared plus 3 squared. Because u squared equals 5 squared plus 3 squared, which is root 34 or 5.83 metres per second to 3 SF. Now we have information about the initial velocity and its component parts, we can find our angle. Doesn't matter which of these we use. I will generally always use sine, simply because if I've got a choice, I tend to use sine first. I don't really know why. It's my favourite when it comes to these problems. But what it does is it technically, for these problems, the sensible thing is to use tan, because you know 3 and 5 are in your problem. So me using sine probably isn't the most sensible, so I probably will actually change it to tan. So tan of alpha will be 5 over 3. So alpha is arctan of 5 over 3, which is 59.0 degrees to 3 SF. I use sine in my working, because I use this exact answer, I got the same answer, and because I was confident that this answer is correct. But this is the sensible way of doing it, so that you're actually using the information of the question. You're not potentially going to get it wrong because you made an error here. But don't worry, if you're confident that you've done this part right, you can obviously use sine or cosine. It's just, I suppose, what technically is the sensible approach. And if you couldn't remember how to do this part, you could still get the answer for that part. So I'd like you to do exercise 6b. Because it's quite a short exercise, you can do the whole exercise. And this is really quite a basic introduction to when we start looking at the harder problems, when we're actually looking at the impact of gravity on the components over time. Okay? So yeah, exercise 6b, whole lot, and we'll look at some of the harder problems as we go through the week.